Guys at home, can I get a thumbs up that you hear and see the board okay? Okay, so I'm hoping to finish our notes today, which will complete section 6.1. And then tomorrow, guys, I'm doing it. I'm not making you come to a meet. Tomorrow is just going to be finish up the 6.1 homeworks that are due. I actually think that the last one that I assigned is due tonight. And then the one that I assigned today, I didn't make due until Sunday night. So it gives you tomorrow in class and the weekend to complete the last homework, all right? All right, so let's do this. Let's get rocky here. Okay. So the last part, we left off with the area of a sector, which is just a fractional portion of the entire area of the circle, just depending on how many degrees or radians you have out of the total. All right, the last thing we have to do is linear speed of an object traveling in circular motion, okay? All right, so first of all, I need you guys to remember the relationship between distance, rate, which is your speed, and time. And the formula always says that your distance will be equal to your rate times your time, right? You go 50 miles per hour for 2 hours, 50 times 2, you got 100 miles. Well, we can manipulate this formula to isolate the rate. If I wanted to figure out, well, what is the rate equal to in relationship to distance and time? Your rate is going to be equal to the distance you traveled divided by the time you traveled for. Okay, so basically we're going to take this relationship about rate or speed and apply it to circular motion, all right? So in terms of a circle, the distance traveled on or around a circle is called the arc length S, and we've already been dealing with the arc length. So guys, when you're traveling in a circular motion, how far you get is literally going to be the length of that arc. It's going to be S. So distance is S. All right, so the speed at which an object moves around the circle is called its linear speed, and we use V to denote it. So the speed at which an object moves around the circle, linear speed, V, it will depend on how far the object traveled, S, arc length, and the amount of time it traveled for. So guys, when you're moving in a circular motion, you have, let's say the object started here, it travels, that's how far it got, so its distance is S, and then it's all about, well, what time elapsed? How much time did he travel for that distance? So his linear speed, V, will be equal to how far did he travel, S, divided by how much time did it take him. So guys, it's literally your rate is equal to your distance divided by time, but your distance is an arc length now. That's the only difference. Otherwise, it's the exact same formula. But we don't use R for rate anymore because it will be confusing with radius. So we don't use R for rate, we use V for your speed. All right, so again, it's an arc length over a unit of time. So when you are trying to find an object's linear speed, you should be in things like inches per second or feet per minute, right? Or we could say centimeters per hour. But that's the unit that you should be measuring linear speed in because it's an arc length over a period of time. So this formula finds how fast an object's position is changing or how fast the arc length is changing. Guys, basically, it's calculating the object's rate. How fast is that object moving around the circle? Okay, so that's one speed that we'll be calculating, the actual object's rate. But then we're going to be calculating an angle's rate as well. So to find how fast a central angle is changing as an object travels around a circle, that's called your angular speed, and we use the Greek letter omega to represent that speed. So again, this is the object speed, the linear speed, and this is going to be the angle speed, omega. So the angular speed will depend on the measure of the angle and the amount of time elapsed as it was swept out. So guys, now as an object travels on the outside, an angle is formed on the inside of the circle. So we call that the central angle, which we'll say is theta. So now what the angular speed is going to do is it's going to calculate, as that object is moving, how fast is the angle inside being formed. So this is from the object's point of view. This is from the angle's point of view. What is the rate at which this angle is being swept out or created? All right? So in order to calculate that, you have to know, well, how big did the angle get? And what was the time elapsed? So the angular speed, omega, will be equal to how big did the angle get, theta, and then how much time did it take to create the angle of that size, t. All right, so this will be an angle measure in radians over a unit of time. So the only really way you should be measuring the angular speed is radians, I just say rads, per second, or maybe it's going to be rads per minute, or maybe it'll be rads per hour. But the important thing is, if you are going to be working with angular speed, you definitely want to be in the unit measurement of radians over some unit of time. All right, so again, this is the formula finds how fast the measure of the angle is changing. So this is calculating, basically guys, it's a rotational speed. How fast is something opening? How fast is something rotating? Okay, so guys, if it represents a rotational speed, in some of tonight's homework problems, they may not flat out say, oh, the angular speed is this, but they might tell you revolutions per minute or revolutions per second. Guys, revolutions is a rotation. So when they talk about revolutions per unit of time, they're literally telling you the angular speed, it's just not in the unit that you want it. So we'll just use a conversion factor to convert it from revolutions per unit of time to radians per unit of time. So when they give you revolutions, they are trying to give you an angular speed. It just needs to be like twerked a little bit, okay? All right, so again, if they're going to talk about revolutions per unit of time, if they're going to talk about revolutions per unit of time, they are gifting you an angular speed. It's just not in the right unit of measurement. Okay? We'll just always convert that to rads, radians per unit of time. Okay? Okay. So those are your two main formulas. You're going to be asked about linear speed, the speed of the object, and then you're going to be asked about angular speed, the speed of the angle, the rotational speed. Well, guys, using substitution, it can then be shown that your linear speed, your v, is dependent on the radius of the circle and how fast the object is rotating. Which, guys, how fast the object is rotating, that's your angular speed. So they're telling you that basically you can rework the linear speed formula to show that it's actually dependent on the radius and the angular speed. So watch this. Take your linear speed formula, right? Your linear speed said that the speed of the object will be equal to the length of that arc, the distance it traveled, divided by time. Well, guys, hold on. Arc length. Right? Arc length, radius, and an angle. We measure an angle in radians by saying the angle is equal to the length of the arc, S, divided by how many radiuses fit into the length of that arc. We literally measure the angle in radians by taking the arc and dividing it by the radius. So if I solve this for S, cross multiply, we had another formula that first day that said S, the arc length, is equal to theta times the radius. So take that formula, theta times radius, and put it in for S. So now instead of the arc length divided by time, now we're saying that the linear speed is equal to theta times radius divided by time. Well, let me just rewrite this as r times theta over t. Just switch the order. Well, now, guys, look at this. Theta divided by time is omega. Theta divided by time is your angular speed. So now we can say it's equal to the radius times omega. So now your linear speed, you have another formula that uses different information to calculate it. So now we can say not only is V equal to S divided by T, another formula for your linear speed will be radius times omega. So that's the formula I want to put in this box, but I don't want to move my notes yet. So in that box, your new formula is linear speed is equal to R times omega, where R equals the radius. Remember, R is not a rate. We don't use R for rate because we don't want to confuse it with the radius. And omega is the angular speed, the rotational speed. Okay, so whenever you're asked to find the linear speed in some of these problems, you have two formula choices. You can use R times omega, or you can use S divided by T. Depending on what information the problem gave you, one formula might be better than the other, okay? All right, let's put this to good use, do a couple examples, and we'll be done. Okay, so this example says an object is traveling on a circle with radius 5 centimeters. Guys, I'm a visual person, so right away I'm already visualing. I got a circle, it's got a radius of 5 centimeters, and we have an object traveling on that circle. So obviously the distance that that object traveled is S, it's the arc length, right? And then an angle will have been formed wherever the object got to. All right, if in 20 seconds, just trying to organize my information as we go, if in 20 seconds a central angle of 1/3 radian is swept out, what is the angular speed of the object is what they've asked you to find first. So as this object traveled on the outside of the circle, an angle was being formed on the inside, and wherever this object stopped, they didn't tell us the distance it traveled. They didn't tell us S, but they did said, however far it got, it's only 1/3 of a radian. So obviously my angle's way too big, but either way, it gets the job done. All right, they want us to find the angular speed. Well, guys, we said omega, the angular speed, will be equal to the measure of the angle. We know how big it got. It got to 1/3 radian, divided by the amount of time it took to make the angle that size. We know all of that information. It took 20 seconds, and it got to 1/3 radian. Plug it in. So it got to 1/3, and it was 20 seconds. And again, if you notice, omega is supposed to be measured in radians, which I'll just say rads, per unit of time. And it is. It's in rads per second. All right, now we just got to clean this up. So I'm just going to times by 1/20, times by 1/20, and you get omega is equal to 1/60. So your angular speed is 1/60th rads per second. And that's easy, nice and done. Just use the formula. Okay, well then they asked you, what's the linear speed? So now we're trying to figure out, well, that's how fast the angle is being swept out and rotating, but how fast is the object moving itself to create the angle at this rate? Well, guys, you have two options for linear speed. We have the original formula that says it's S divided by T, right? The length of the arc divided by time, but we don't know S, right? But we have another formula that says linear speed can be found using the radius times omega, the angular speed. I know the radius, I know the angular speed, here's your better formula. So I'm not going to use that one. I'm going to use this one for your linear speed. So V equals, what was the radius? Because that's what R is. It was 5 centimeters. Times, what was your omega, your angular speed? It was 1 over 60. That's 5 over 60, which is 1/12. So now your unit of measurement. Well, guys, linear speed is literally the distance the object traveled per unit of time. So the radius and the object are always measured in the same unit. So your radius was 5 centimeters, right? So this is centimeters. This is rads per second, but usually remember, rads don't get labeled. So you have rads per second, so this becomes centimeter per second. So its speed at a linear rate is 1/12 centimeters per second. And that's the speed of your object. Is everybody okay with that? Now again, you could probably use this formula if you substituted S equals theta times radius over time. Then you might have enough information to go off of. But why when this formula is made so simple for you? Okay? All right, let's try the last one, and then we're done. All right, this one said, first of all, everybody at home, can I get a thumbs up? We're okay? We're good? Oh, wait, I heard a hand. What's that, Michael?
What is it? I can't see what it says, like where it says V equals 5 and then in parentheses 1 over 60.
So I put 5, the radius was measured in centimeters. I'm trying to get you to your unit. So 5 was measured in centimeters, and then your angular speed was measured in radians per second. But again, normally we don't label radians, so this becomes centimeters per second. Just in case they make you label anything. I think one question literally talks about the unit of measurement, so I just wanted to show you how to get there. Because your angular speed, omega, was radians per second, but this is measured in centimeters per second. Is that what you were asking, Michael, what I was reading?
Yeah.
Okay. I was just trying to put the measurements in so you could see what your label is, your unit.
Yeah, thank you.
You're welcome. All right, last one. A child is spinning a rock at the end of a 2-foot rope at the rate of 180 revolutions per minute. So guys, this is what I'm talking about. I think there's quite a few problems that talk about revolutions per unit of time. Remember, when they give you this information, they're sneaking in angular speed. That's a rotational speed. It's just not in radians per unit of time like we like. But we'll be able to convert that to radians per unit of time. So they have snuck in omega. That's an angular speed right there. That's a rotation. But they asked you to find the linear speed of the rock when it is released, right? So guys, we have radius and we have an angular speed, and they've asked you to find linear speed. Well, remember, V is equal to S divided by T, the distance the object traveled, the arc length divided by time, or V is equal to radius times omega. We got the radius. The radius is a 2-foot rope there. Omega was given to us, it's just not usable yet. So I'm definitely going to use this formula. I just got to get all my ducks in a row. I got to get everything in the right form. All right, so I know my radius is 2. That's good. Omega. Omega right now is equal to 180 revolutions per 1 minute. That's how they've given you your angular speed right now. Okay. We need the angular speed to be measured in radians per minute. So I need revolutions to cancel. So guys, think about what we know. How can we convert this? Well, they're talking about revolutions, right? So I need revolutions to be on bottom so my revs will cancel. Well, guys, the easiest revolution to talk about is 1. 1 revolution is equivalent to how many radians? How many radians live in 1 complete revolution or rotation around the circle? 6.28, which is the estimated. What's the exact form? 2 pi. So we know 1 revolution will consist of 2 pi radians. So that's your conversion factor. You can always take revolutions per any unit of time and change them to radians per unit of time by using 2 pi over 1. So now your revolutions will cancel and you will be in radians per minute. So multiply across, 180 times 2 pi is 360 pi over 1 times 1 is 1, which is literally just 360 pi. And now you're going to be in radians per minute. So guys, now we have everything we need. We have a radius, it's 2. We have an angular speed, it's 360 pi radians per minute. Plug it in. So V will equal R times omega. Who's R? 2. Omega is 360 pi. And then we multiply, we get 720 pi. Now again, just watch the questions. Do they tell you to put the exact answer of 720 pi, or do they tell you to round to a couple decimal places? Just pay attention. I'm going to leave it exact. But otherwise, you would just do 720 times pi. And I believe there's a question that literally tells you, normally I just use the pi button when I want to use pi, but somewhere, I think in one of the homework problems, they give you use 3.14159 for pi. So they actually tell you a number to use for pi. All right, and then what's the measurement going to be? For linear speed, remember, that's the speed of the object. So it should be like a distance measurement over time, like inches per second, miles per hour. This is going to be, what was your radius measured in? Feet. Your angular speed was rads per minute. So now this will be, we really don't label rads, this will be feet per minute is what your linear speed is. And you're done. So again, I think there's a couple problems that definitely talk about revolutions. Guys, they are sneaking that angular speed in. It just needs to be converted to rads per unit of time. All right, how do you guys feel? Okay? Fine? All right, at home, are we okay? Yes? Okay. So guys, that's 6.1. It's a lot. And like I said, it starts off with just some really important information. Radians and those really important radian angles that we went over yesterday. All those specials, multiples of 30, 60, 45. All right, so the homework on this, I didn't make due until Sunday night. So I'm giving you tomorrow in class. Guys, there'll be no meet tomorrow. I'm not going to make you log on. I'll probably have to post an attendance question though. So you'll have an attendance question, and then you work on your homework. I'll be on the meet in case you need me, or you can just text me or whatever, but I'll be there to help, and then your homework is due on Sunday night. So you have tomorrow and the weekend to get the last homework done, okay? All right, let me double check your attendance.